Welcome back to video 4, everyone. I hope the virtual in-class exercise went really well, and I'm glad you're here for part 4 of modules 7.1 and 7.2, where we are going to be talking about the closure and minimal cover of F. Now, as we mentioned in a previous video, our set of semantically obvious functional dependencies is a set we call F. And the closure of F, or F closure, includes all of these semantically obvious functional dependencies, as well as all other functional dependencies we can infer based on the semantically obvious functional dependencies. So we use Armstrong's axioms to help us derive all of the functional dependencies that are in the closure of F. So, for example, given a set of semantically obvious functional dependencies, so these are the functional dependencies that were described by our business users, we have these two functional dependencies, store and product functionally determine quantity, and then quantity functionally determines discount. So, based on FD1 and FD2, using transitivity, we can infer the presence of a third functional dependency, which is that store and product together functionally determine discount. Okay, so this would be another functional dependency in the closure of F. Now, note that since trivial dependencies, things like quantity determines quantity and discount determines discount, doesn't provide any additional information, we usually don't bother repeating these when we are making the closure of F. So now going back to our stock example, where we had these 4 semantically obvious functional dependencies of store functionally determines location, square footage, and manager, store and product together functionally determine quantity, product determines price, and quantity determines discount. These are our obvious functional dependencies because this is what was stated in the business case. From these 4 semantically obvious functional dependencies, we can use Armstrong's axioms to find many more functional dependencies that are in the closure of F. For example, we could decompose functional dependency 1 to create 3 new functional dependencies of store determines location, store determines square feet, and store determines manager. We could also use the transitivity axiom to say store and product together determine discount. That's transitivity between functional dependency 2 and functional dependency 4. We could use composition of FD1 and FD3 to say store and product together can be used to functionally determine location and price. Or we could do composition of functional dependency 3 and 4 and say product and quantity together can functionally determine price and discount together. Okay, this is just a small sample of some of the functional dependencies that would be found in the closure of F. Now, this is the really important part. The problem, what causes undesirable functional dependencies, is when the determinant in the functional dependency is not a candidate key in the relation. Okay, this is so important. Let me say it again. An undesirable functional dependency is when the determinant in the functional dependency is not a candidate key in the relation. Okay, that's what we have to resolve. That's what causes our data redundancy and what causes our modification anomalies. So in our stock example, recall that we said this combination of these two attributes, store and product, can uniquely identify every tuple. Therefore, it's a super key, it's a candidate key, and we've just said we're going to select it as our primary key. But then the semantically obvious functional dependencies are that product functionally determines price. Well, product is not a candidate key. So that is why we have redundancy in our price attribute, because price is being functionally determined by an attribute that is not a candidate key. Okay? This functional dependency that quantity determines discount, quantity is not a candidate key. So this is an undesirable functional dependency, and this is why we have redundancy in this discount attribute. And finally, the functional dependency that store functionally determines location, square feet, and manager. Store, again, is not a candidate key. It's a key attribute. It's a proper subset of a candidate key, but store is not a candidate key, and that's why we have problematic data redundancy in these attributes location, square feet, and manager. And what we did to resolve this was to decompose this relation into these four smaller relations. So we basically just took our problematic functional dependencies and we moved those functional dependencies and all the attributes involved in those functional dependencies out into new relations. And we did this a few videos ago just because it kind of intuitively made sense. This is why it resolves the issue, and in the next set of videos we're going to see the process that we systematically go through to apply Armstrong's axioms to really understand how we break apart this relation to get rid of problematic functional dependencies and get rid of data redundancy. Okay? So stay tuned for the next set of videos for more examples of that. It gets good, guys. Now, one more thing we need to talk about before we get into that is the minimal cover. Okay, so whereas the closure of F is every possible functional dependency we can infer from the set of semantically obvious functional dependencies, our minimal cover reduces the semantically obvious functional dependencies to a smaller number of functional dependencies that still capture everything that was stated in our business case. And the reason this exists is because just like we talked about designing our entity relationship diagram being an iterative process and that our users often don't say exactly what they mean, one thing you will find is that often stated functional dependencies have some redundancy in them in that we may state three functional dependencies and one of them is kind of captured by one of the other functional dependencies. So it can make things simpler to find a smaller number of functional dependencies that still captures all of our business rules. Now, here's an example of that. Imagine we were designing a database for an apartment complex. Okay, so we have a relation that has these three attributes: tenant, apartment, and rent. And as the apartment complex owner is describing to us how they understand their data, they say something like, okay, well, if you tell me the name of a tenant, I can tell you what apartment they're in and how much rent they pay. Also, if you just tell me the apartment number, I could tell you how much rent I charge for that apartment. If you were to tell me the name of a tenant and the apartment that they are staying in, I can tell you how much rent they pay for that apartment. And if you just tell me the name of a tenant and how much rent they're paying, I could use that to look up the apartment that they're renting from me. Okay? So this is how the landlord envisions their business process. And you may already see that there is a little bit of overlap in these functional dependencies, but we're going to use Armstrong's axioms to systematically figure that out. So the first thing I would point out is that we can decompose our semantically obvious functional dependencies, or we can modify them to simplify things. So let's decompose functional dependency 1 into two functional dependencies: tenant determines apartment and tenant determines rent. Okay, this is our decomposition rule. Now, we could do this really in any order that makes sense to us, but I'm going to start here, especially since pseudo-transitivity is my favorite. Since we see in functional dependency 1b that tenant functionally determines rent, well, in functional dependency 4, that means we could replace the word or the attribute rent with the attribute tenant, which just turns into tenant and tenant together determines apartment. Which we don't need tenant twice. That's just tenant determines apartment. Well, turns out that's already what functional dependency 1A is. Tenant functionally determines apartment. So functional dependency 4 is really saying the same thing that FD1A is saying. So that's just a kind of superfluous functional dependency, and we can eliminate that because we're already capturing that in FD1A. So now we're down to this, and let's use pseudo-transitivity again. In FD1A, since tenant determines apartment, we have a similar situation here in functional dependency 3. So what this is really saying is tenant and tenant, or just tenant, determines rent, which is the same thing we have in functional dependency 1B. So FD3 is just a superfluous extra functional dependency. We can get rid of that. Now we're down to this. And our transitivity axiom says that tenant determines apartment, and then apartment determines rent. So if tenant determines apartment and apartment determines rent, then tenant determines rent, which is what functional dependency 1B says. So that's actually extra as well. And now at this point, we're down to just 2 functional dependencies that actually capture everything that our apartment manager is trying to do. So we started here with this big kind of messy group of functional dependencies, but we can capture all of these rules with just these 2 functional dependencies of tenant determines apartment and apartment determines rent. Okay? So there are some other examples in Chapter 7. I would strongly encourage you to work through those and write them out and make sure you understand that. We'll do more examples like this in our future videos and in section 7.3. And we're going to be showing how we can use Armstrong's axioms to systematically identify candidate keys. And then once we do that, how we break relations apart into smaller relations to get rid of our data redundancies. So in the meantime, you guys stay safe, wash your hands, don't touch your face, and stay home and do great things. See you next time.